Could you actually create life from pure light? I know, it sounds like something straight out of science fiction. But what if I told you there's a serious research plan to figure out if it's possible? Today, we're going to dive into how you take an idea from a Star Trek episode and turn it into a real-world experiment. Let's get into it.
So, the spark for this entire incredible project comes from a place you might not expect, a single episode of Star Trek Voyager. The researchers literally call this their cultural trigger. It's that moment when a wild idea from a TV show makes a physicist stop and ask a very, very serious question. Hang on a second. Could that actually work?
And that's the real question, isn't it? I mean, how do you take a concept as out there as photonic life and actually translate it into something you can build and poke and measure on a lab bench? Well, this research framework is their roadmap for trying to do exactly that. So how do you even begin to go from a sci-fi script to a serious scientific protocol? Well, you start by taking that big, imaginative idea and you break it down into small, testable questions.
The researchers basically boiled down this huge concept of photonic life into 3 core fundamental questions. Now, answering these isn't going to create a new life form, but it will tell us if the basic building blocks are even possible under the laws of physics as we know them.
It really all comes down to these 3 hurdles. First off, can we even get particles of light, photons, to interact with each other? Because normally, they just pass right through one another, completely ignoring each other. Second, if we can get them to interact, will they start to self-organize into stable, complex patterns? And third, and this is a big one, could we build a kind of life support system to maintain those light patterns without having to pump in a ridiculous amount of energy?
Okay, so to answer those questions, the plan lays out 3 totally distinct experimental tracks. Each one is designed to tackle one piece of this massive puzzle. So let's head inside the virtual lab and start with Track A.
Track A is all about solving that very first problem. How do you get photons, which are basically the introverts of the particle world, to actually interact? The goal here is to make them social, to force them to at least acknowledge that other photons exist.
And here is the absolutely brilliant solution they've come up with. They use something called a Rydberg EIT medium. The easiest way to think about it is like a special gas. When you zap its atoms with lasers in just the right way, it becomes a sort of moderator that forces the photons passing through it to influence one another, almost as if they had mass. So the experiment itself is pretty straightforward. You send little pulses of light through this special gas and just see what comes out the other side. Success here means seeing something called photon bunching. Think of it like this. If you have people walking through a narrow doorway, one at a time, that's normal. But if they suddenly start coming out in pairs or little groups, you know something inside that doorway is making them interact. That's photon bunching. It's the smoking gun that proves they're not ignoring each other anymore.
Okay, so let's say we can make photons interact. Now what? Where do you even put them? Well, Track B is all about building the environment, a kind of photonic petri dish, if you will, where these newly social photons can be contained and watched.
And for this job, they're proposing something called an ENZ cavity. This is a really advanced metamaterial that's been specifically engineered to, well, trap light. Inside this little box, light slows down like crazy, which gives it the time and the space it needs to potentially self-organize into those stable patterns they're hoping to see. The experiment is just beautiful in its simplicity. Fire a laser pulse into the trap and film what happens with a super-fast camera. Now, what's really fascinating here is the success metric. They're not looking for something that lasts forever. Success is defined as a stable pattern that holds its shape for just 1 microsecond. I know, that sounds like nothing to us, but in the world of light, a microsecond is an eternity. All right, now for the third and maybe the most crucial piece of the puzzle, homeostasis. If you manage to create a delicate, beautiful pattern of light, how in the world do you keep it from just fading away? Track C is all about designing an active life support system to do just that. They call it the laser agent loop. It's actually a pretty simple feedback system. You have a camera that watches the light pattern. A small computer sees the image, and if it notices the pattern is starting to fall apart, it makes tiny, precise adjustments to the main laser to kind of nudge it back into shape. It's a perception-action loop, but for light. The goal here is to prove that this feedback loop actually works, and they've set a very specific and very tough target. The loop has to extend the pattern's lifetime by at least 3 times. And get this, it has to do it using 10% or less extra energy. So it's not enough to just keep it alive. You have to do it efficiently.
Now, whenever you're dealing with frontier science like this, there's a huge responsibility to be rigorous, to be safe, and to be transparent. The researchers here go to great lengths to define the rules of the game before they even start playing.
This right here, this is a go-no-go table. And honestly, this is what good science looks like. Before a single laser was fired, they pre-registered exactly what counts as success for each track. For track B, if a pattern lasts longer than a microsecond, it's a go. If it doesn't, it's a no-go. End of story. This keeps them honest and prevents them from moving the goalposts later on.
They also lay out the entire ethos of the project, crystal clear. This research is meant only for peaceful purposes. All the data will be open for anyone and everyone to see. And the methods are deliberately cautious, capping laser power to ensure safety. They are making it very plain. This is not about building laser weapons, it's about fundamental discovery.
So, with all these experiments and all these rules, what would a win actually look like? Well, it's really important to be clear about this. The goal here is not to create some sentient being made of light. The ambitions are actually much more fundamental and in a lot of ways, way more interesting.
A massive win would be hitting this number from track C, proving that you can use an intelligent, low-energy feedback loop to extend the life of a complex optical pattern by 3 times or more. That would be a monumental breakthrough.
And that really brings us to the ultimate point. Because when you strip it all away, this project isn't really searching for life. It's searching for the answer to a much deeper question in physics. What is the absolute minimum energy cost to create and sustain complex order? Answering that question, well, that could unlock breakthroughs in everything from optical computing to next-generation material science. And that's where we're going to leave it. This entire research framework, which was literally sparked by an episode of Star Trek, is pushing us to reconsider the fundamental nature of light itself. Because if something as familiar as light can be nudged towards this kind of complexity and self-organization, it really makes you wonder, what other basic properties of our universe have we been completely overlooking this whole time?